Hi everyone. Thanks for having me. I understand you guys have been learning a bit about the atomic structure and the periodic table in your chemistry lessons. So today I'm going to talk about the periodic table in medicine and try and kind of escape this idea of elements as these abstract things that are just on the periodic table, and try and explain how they're applied in day-to-day life, particularly by doctors and by researchers. So in terms of our learning objectives today, hopefully you will know, or you'll have been studying the difference between atoms and compounds. I'm going to go over that very briefly just to kind of recap, but then try and look more broadly at how these elements, these atoms, these compounds are applied in the wider world of medicine. And finally talk about how medicinal chemists like myself use these things to research particular disease treatments. You guys should have all hopefully had a pre-lesson pack. I just wanted to check there weren't too many issues with those or too many questions. If you guys want to fire anything into the chat, I'll hopefully be able to answer as we go by. But there are a few questions at the end, so I don't know if you guys have gone through them yet, but just wanted to go through the answers. So 2 letters that don't appear on the periodic table, maybe discuss amongst yourselves very briefly. And I'm not sure if you guys have got this right or not, but the 2 letters JQ are the only 2. And a bit of a silly one: which element hates banks? One of those rogue elements whose name doesn't match up to its symbol, but that's antimony, antimony. Those are that's the element that hates banks. In terms of a favorite element, you guys can hopefully discuss amongst yourselves, but I'll just say my favorite element is phosphorus. I'd pick that because it's, it forms the backbone of DNA, so human life wouldn't be possible without phosphorus. But in terms of impact in its day-to-day life outside of DNA, it's in all kinds of foods and fertilizers, and I use it lots in the lab to try and make molecules. Finally, these 4 molecules, linking it to its name, we can see here. So these are some, I'm sure, molecules you'll all have encountered. So caffeine, paracetamol, nicotine, and penicillin, and this is what they look like. Hopefully these skeletal structures aren't too confusing. There should be something in your pre-lesson pack about what this means. But again, any questions, do feel free to fire them in. So yeah, so that was just a little teaser, taster. And so looking ahead, or moving on in terms of looking at atomic structure and the periodic table, I think it's important to consider how everything fits into each other in terms of building blocks. So what can we break things down into? The first thing we get to is subatomic particles. You might have come across these, you might have not, but in any case, it's important to know that atoms are made up of these things called protons, neutrons, and electrons. And there's some reference to these on the periodic table. You can see the numbers on the periodic table. The smaller number corresponds to how many protons are in an atom, and the bigger number corresponds to how many protons and neutrons there are. And these are important because they govern how elements behave, how they react, and so they're important day to day. Building up from that, we get to atoms and elements. Now, you should all know that atoms are kind of the smallest constituent part of a substance. And an element is a substance that can't be broken down into any other substance. So it can be one atom of that element, or it can be hundreds of the same atom, but these all form elements. And then building up, we get from elements into compounds, and simple compounds and simple molecules. So there's a few here that you'll have heard of: water, carbon dioxide, methane, ammonia. So compounds are substances that contain atoms of 2 or more different elements joined together by a chemical bond. And then we can build that up even further into more complex molecules. So things like drugs that you might take, medicines you might take, and then even more complex molecules like proteins and different things within your cells. Today, I'm going to try, as I said before, we're going to try and move elements away from this kind of abstract thing that you just see on a periodic table, and try and understand how they apply more widely to the world of medicine, and pick out a few examples that doctors use day to day and that are really important for patients around the world. So I'm sure you're all aware and all you're all knowledgeable of the periodic table. But briefly amongst yourselves, maybe try and guess how many of these elements are used in medicine, and see if you can pick out a few that you might be aware of, or try and guess which ones are important and why they're important. So I'll give you a few seconds just to talk amongst yourselves and come up with how many you think, and in particular which ones are important and why. So I'll leave you for a few seconds.
Remember, guys, you can put that in discuss it amongst yourselves, and then the teacher can relay the information through the chat box. We just put it in there. I'm testing my knowledge on chemistry here, Rob.
Sorry. I'm sure there'll be a few that are familiar to you.
Definitely a few, yeah, for sure. Oh, and just to let you know as well, I do have some questions that have been sent in already,
Right.
and I've got them at the end. We've got some nice ones actually.
Yeah, for sure.
Got a couple of answers. Somebody said 45, and somebody else has said non-metallic elements.
Okay.
That'll be that is the two groups that we've got.
All right, 45 non-metallic elements. There's definitely some non-metallic elements that are used in medicine, that's for sure. I personally counted 30, though if you can tell me the other 15, that would be useful for my my PhD, that's for sure. But I've just highlighted 30 elements or so here that are used in medicine. I'm sure you know, some of them will make sense. Obviously, oxygen is very useful, calcium for your bones, things like nitrogen are good in carbon, etc. There's maybe some that you're not aware of, like platinum, samarium, bismuth. They're all so obviously these kind of obscure elements that you don't really deal with in the periodic table. They're all down the bottom. You don't really want to talk about. They're actually really important in medicine, and they can be very helpful for patients across the world. So I'm going to take a few examples here and just kind of talk through why they're important, why they're useful. So the first one I'm going to talk about is lithium. You've probably seen lithium in things like flame tests. You know, if you set it on fire, it burns with a nice red flame. But you've also probably seen it when you dunk it into some water. If you've not seen lithium, you'll have definitely seen elements that are very similar, things like sodium and potassium. When you chuck these in water, they smoke and they react very violently. But often we don't really deal with lithium beyond that. But it's really useful as an element. You know, it's in lithium ion batteries, for one, so in your phones and everything like that. Without lithium, you wouldn't be able to use it. But importantly, in medicine, it's used in a compound called lithium carbonate, which is a really important compound for psychiatric disorders. It's actually discovered by an Australian doctor because he thought that you could cure psychiatric disorders with the urine of healthy patients. So he was injecting guinea pigs with the urine of healthy people and found that sometimes the urine was quite cloudy, things weren't dissolving properly. So he added lithium carbonate to the urine and injected it into guinea pigs and found that it made them really docile. And that was how they discovered that lithium carbonate could be used to treat psychiatric disorders. And since then it's been used, so since the 1840s, I think, the 1840s or so, it's been used as a compound to treat psychiatric disorders. So it's seriously important and not just something you dunk in water to make explode. Here's an element you might not have come across, gadolinium. So that's right down the bottom of your periodic table, GD. Gadolinium, a bit of a rogue one, part of the lanthanides. You don't really talk about it much, but it's really good at absorbing radiation. So they use it in nuclear reactors to shield people. But in medicine, it's used as a thing called a contrast agent for MRI scanning. Now, I'm sure you've all heard of MRI scanning. Knowing how it works is quite complicated. But essentially what MRIs look at is water in your body. Now, you can understand that might be a bit tricky because obviously we're 70% or so water. So how do you tell the difference between water that's, say, in your brain or in your bones, etc.? So what gadolinium does is it provides a way of seeing the difference because it's absorbed at different rates by different tissues. So gadolinium can be used to provide contrast. And you can see in that picture up the top right, before and after you add gadolinium, there's not really much you can see on the left, but on the right, suddenly these areas are lighting up. And gadolinium helps doctors to see tumors and things like that. So it's really important for MRI scanning. Finally, just going to talk about fluorine. So fluorine, the 9th element, exists as a very pale gas, and it's actually really, really dangerous as a gas. But you might have encountered it as fluoride, which is in your toothpaste and in the water. So it helps keep your teeth healthy as fluoride, but as fluorine, it's not very nice at all. So avoid it if you can. But in medicine, it's used in a thing called positron emission tomography or PET scanning, which is another form of imaging. Essentially, what this involves is taking glucose, which has some fluorine in it, and using the fact that things like tumors take up glucose at a different rate or a higher rate to other tissues in the body. It means that the PET imager can see the fluorine that's in the glucose that's being absorbed by the tumors, and it allows you to see where the tumors are in the body. So you can see here on the right-hand side, a PET image where someone's got tumors in their liver, and the glucose that's being taken up by these tumors is being as lit up because the fluorine is being shown by this PET imaging. The brain and the bladder are also lit up because your brain naturally uses more glucose than anywhere else in the body, just because it's working hard all the time. And the bladder's lit up because once glucose is taken in, some of it is immediately cleared in your urine. So you'll always see the brain and the bladder light up. However, here it's used to show a tumor in the liver. So it's really important for that. And these compounds are things that are really saving people's lives. So moving beyond the periodic table, you can see just how important elements can be. I'm just going to talk briefly about kind of more complex compounds, things like drugs and proteins. Anyone got any idea what this drug is? You'll all have taken it, I'm sure, at some point in your life. I'll be impressed if you can get it, but fire in your ideas or just chat amongst yourselves of what drug you might. It's used for pain relief. I'm sure you'll all have taken it.
Paracetamol, somebody's put in?
Close. It's not paracetamol, but it is close. It's ibuprofen. So I'm sure you'll all have taken it. But this is kind of getting close to what my job is day to day. It's trying to make molecules like this that help patients. So my job as a medicinal chemist is to use chemistry and techniques in chemistry to bring the different building blocks together, so the different elements together, into more complex molecules like drugs, like ibuprofen, that can be used to help patients. And often one building block, so one element, can be the difference between a drug working or not. So in this instance with ibuprofen, if you didn't have these oxygens here, then it wouldn't work at all. So these oxygens are not just important in terms of oxygen that we breathe or whatever else. Actually, oxygen can be a really important part of lots of drug molecules, and elements in general are very important as part of drug molecules. So hopefully that explains how, or kind of removes elements from this abstract thing on the periodic table into something a bit more tangible and something that you guys interact with day to day and people interact with day to day. And
with that, Rob, we've got a curveball question here for you.
Oh yeah, go on.
If you know the answer to this, I think you might be making a lot of money in the near future. Do you know which atoms have been used to make the COVID-19 vaccine?
Well, so that's an interesting one, because the COVID-19 vaccine that's just been announced as being successful is actually a thing called an RNA vaccine. So in your cells, you have DNA, as I'm sure you're all aware, and the DNA is a little code for life, basically. So along your DNA, which is hundreds of thousands of different codes long, you have all the codes for everything you need. The way this works is that the DNA is read and it's turned into a thing called RNA, and RNA is what's used to make proteins. So the vaccine in question uses RNA, an RNA which codes for the spike protein in COVID. So if you ran the RNA through a little protein maker that the vaccine's made of, it would make the spike protein. When you give it to a human being, your own cells start making the spike protein. Then your immune system can recognize it, develop antibodies against it, and then when you actually get infected by COVID and it recognizes the spike protein, you'll already have the antibodies and you'll be able to, you'll be immune to it. So that's, the molecule itself is called RNA. In terms of the atoms that make up RNA, carbon, oxygen, nitrogen, phosphorus, so they're all involved and they're all very important. So that's how the RNA vaccine for COVID works.
Interesting. Cool.
Yeah, so that was the end of my chemistry. If you guys have any other questions or you want to ask any questions about drugs, etc., please, or molecules, then fire away before I get into kind of more conversations about my career path and how I got into what I do. So I think
I did say I had some questions that were sent in. So guys, obviously think about questions that you've got about chemistry, and I've got a couple here. Here's a good one. How heavy is an atom?
That's a good question. So an atom is kind of intangibly heavy, really. It doesn't weigh anything in terms of, like, you know, if you had a bag of sugar, which is a kilo, an atom doesn't really weigh anything at all. However, we talk about a thing called molecular weight. So it's a kind of abstract way of understanding how heavy an atom is. And an atom's weight depends on how many protons and how many neutrons it has. So if you look at your handout, you should see that kind of subatomic structure with protons and neutrons. And so an atom's weight, it depends on how many of each it has. And if you look in the periodic table, there should be two numbers. So there should be numbers that go up by one every time as you go along it. But there's also numbers that are a bit bigger and they're kind of decimal places. So that number denotes how heavy each atom of an element is relative to one another. So for example, hydrogen is 2, and lithium is 3, and then helium is 4. So helium is twice as heavy as hydrogen, but you can't really look at it in terms of weights as we would talk about them in general day-to-day life. You're not going to be talking about grams of an atom. It's all about relative masses, so how heavy an atom is relative to another atom. But the weight is dependent on how many protons and neutrons an atom has.
And then you've mentioned the periodic table several times. How old is the periodic table?
151 years, is it? I think last year was the 150th year of the periodic table. So I guess 150 and a half or so.
150 and a half. Okay, that's fine. That's good. Somebody has asked, where can I research the theory of the atom?
Wow. Lots of places. You can, school, obviously a great place to start. Going on to university to study physics, to study chemical physics. But there's lots of great textbooks, lots of great books. I guess, you can start looking at, the old work of some physicists like Rutherford, who's one of the first people to kind of split the atom. He would be a good place to start. Look at places like radiation. So people like Marie Curie, who looked at radiation, which is an important kind of theory surrounding atomic structure. People like Einstein and their theories about atoms. So I think, just delve into, Google's a great friend. But in terms of names, I think someone like Rutherford would be a great place to start for that.
And then we've got, okay, so that's good. We've got another question that kind of relates to that and hopefully should lead in nicely into maybe your career and then also careers in the industry of chemistry. Can I have a job in which I look at atomic structure theory?
Yeah, for sure. Nuclear physics is entirely based around atomic structure theory, really. And so there's all kinds of jobs associated with nuclear physics, whether it's working in nuclear energy, whether it's working in defense, whether it's doing fundamental research into nuclear physics. You guys might have heard of CERN, which is in Switzerland, that massive, big, kind of 25-mile long beamline, where they basically just take atoms, speed them up to near the speed of light and smash them into one another to see what happens, which sounds like great fun to me. So you could go into research like that. So there's plenty of ways you can research atomic structure and love it, I'm sure.
Brilliant. Somebody has asked, okay, we've got two questions that have come in. So for that, how much is the salary? That's a tough question, right?
I'm not a nuclear physicist myself, but I'd imagine that, once you're getting up to kind of the top levels of nuclear physics and nuclear power, you'll be earning a fair whack. So I think you'll be comfortable, that's for sure.
So you won't be cancelling Christmas. And do you need a degree to work with the periodic table?
No, not at all. I think anyone can work with the periodic table. Day-to-day life, you're working with the periodic table. If you're cooking, you're working with the periodic table. If you're just existing, you're always working with the periodic table. I think this is what I was trying to get across, is that elements aren't just these things on the periodic table. They're things that exist in life, and we use them every day. So you don't need a degree whatsoever. If you do want to go and work in chemistry, then I think definitely a degree in chemistry will set you up to be able to work in areas like pharmaceuticals, cosmetics, cooking, nuclear chemistry, petroleum chemistry. There's so many areas that use chemistry and use elements. So I think a degree in chemistry or physics and studying at university, or even just studying at A-level, will definitely stand you in good stead. But let's not forget that elements are around us all the time. So whichever job you're going to be in, you'll probably be using the periodic table in some respect. But in terms of chemistry, then I think a degree in chemistry or some facet of chemistry will be very useful.
And there is also a question about whether there is a vocational or apprentice route into chemistry as a career.
Um, that is a good question. I can't say for certain whether or not there is an apprenticeship or anything into chemistry. However, I do know that the vast majority of careers that use chemistry will require a degree in chemistry, but lots of them are kind of industrially supported. So when I say industrially supported, I mean the chemical industry. So whether it's pharmaceuticals, whether it's petrochemistry, they'll support your degree. So the idea being that you study, and then when you finish, you then get to go and work for them. So that's a nice, easy route into industry, into working into chemistry as a vocation.
I suppose, and this is going to be a good area to cover. And remember, please keep bringing your questions in. We have still got time. Excuse me a second. But in terms of that question about a vocational or apprentice route into chemistry as a career, I think is it worth exploring the side that chemistry, there's a lot of careers that use chemistry, right? It's not a small niche market, but you use chemistry across a lot of different industries. If I was to think, and you can correct me if I'm wrong, Rob, but in the construction industry, I'm sure you would use chemistry. In the petrol industry, oil industry, there's a lot that goes on there, and there are a lot of careers that will use chemistry. I am sure that there are apprentice routes into chemistry as a career, but if you do study chemistry, just how many avenues does it open up, Rob? Is it limited?
I honestly think it's unlimited. I mean, you could go on for days talking about which careers use chemistry. You know, just off the top of my head, obviously there's the pharmaceutical industry, there's the petrochemical industry, like you've just said, so working in oil and gas, the cosmetic industry, things like L'Oreal have a massive chemistry division. That's hugely important to them. Cooking, hugely important, and food safety, that's preservatives, farming, fertilizers, feedstocks. Outside of more obvious kind of scientific, there's law requires chemistry a lot. So if you want to be dealing with kind of the intellectual property, if a pharmaceutical company makes a drug and then another one comes along and says, no, this was our idea, law companies need chemists to be able to sort of look through the data and say, oh, actually this was them. So law is a massive one for chemists. Finance is a huge one in terms of understanding healthcare markets and pharmaceutical markets. The list goes on, really. It is unlimited. And also not just chemical knowledge, but the skills that are required for chemistry you can be applied anywhere, into your analytical skills, your problem solving skills. It can be hugely important and it's hugely valuable across a variety of different sectors.
That's a really good thing that you said there about the transferable skills. We've talked about it in other sessions. We've talked about it in other lessons as well, about those transferable skills and what you learn studying one thing, and those techniques or those skills that you learn that can then be transferred to other areas. You're beginning to see that the things that we study, whether it be maths, whether it be English, whether it be chemistry, they're very, very useful in the world after school, because they're applied to so many different things. This is what our world is made up of. Let me ask you, Rob, how did you get into your career in chemistry? Was it something that you enjoyed at school and thought, that's it, that's what I'm going to do, that's where I'm going?
Yeah, I mean, I can talk you through it. I've got a few slides on that, but just as a kind of an introduction, I was really interested in medicine and also really interested in medical science, but and I think as lots of people do, they want a career that's going to be both fulfilling in terms of you being able to make a positive impact, but also interesting in terms of, sort of fostering your kind of enthusiasm for a subject and, keeping you fascinated and interested in the subject. So for me, chemistry ticked all those boxes in the sense that it could be applied to medicine, but also in terms of the theory and everything around it, I found it really fascinating. So that's what propelled me into chemistry. And I think as you get further into it, I think at school often, you do a lot of chemistry, which is quite fundamental, and that's really fascinating. But as you get further along the line of studying chemistry, you do realize how much it's applied to, and you realize just how many avenues there are to go down. So you're not limited at all by just studying chemistry, because it really opens so many doors. And I before I started, I didn't realize I'd be going into kind of proper drug discovery and studying diseases and studying, human biology and all that kind of stuff. I thought, oh, chemistry is chemistry, but actually you realize that chemistry is everywhere and chemistry is in everything. So you're always studying something new and learning something exciting and interesting. So yeah, that was I've not regretted the decision whatsoever. It's been a really fulfilling enterprise so far.
That's good to hear. We've got 1 minute left. Let's see if we've got any more last minute questions coming in. Think of the questions that you have. I mean, we can go a minute over if Rob allows us.
Yeah, for sure. I've got time. Don't worry. I don't want to keep you longer, but I've got time.
Just conscious of the lessons time as well. And one question somebody did ask that was sent in, and you have mentioned about your career and you enjoy what you do. I imagine that you are based in Bucks, but somebody did ask. Sorry, bear with me. Let me just get the Word document up again. Well, the question that is always asked: do you get to travel with your job?
I do, yeah. I mean, that's one of the joys of chemistry, particularly science in general, is conferences. You know, there's all these international conferences and great opportunities to go and present your research and to see cutting edge research, you know, before it's ever come out. So, for example, looking at the COVID vaccine, obviously at the moment, there won't be any kind of travel, you know, for obvious reasons, but you can still attend conferences virtually. And so that data was presented at conferences before it kind of came out in the news. And you get to travel loads. You know, when I was studying in my undergrad at Edinburgh, I got to live for a year in France and work in a research lab there as part of my undergraduate degree. Then since coming to Oxford, I've been to Cincinnati in the US for a conference. I've been to Strasbourg in France for a conference. I've been to the Bahamas for a conference, which was pretty nice. That was just before lockdown as well, so I was quite pleased to get that in. Yeah, and then when it comes to, in terms of not just conferences, you know, chemistry is a global language, right? One of the great things about this skeletal formula that you can see on the slide here of ibuprofen is that I can show that to someone in Russia, I can show that to someone in China, I can show that to someone in Colombia. And if they've studied chemistry, they'll know exactly what that means. You know, it's an international language. You can go anywhere with it. You can do it anywhere. So once you've, you know, graduated, you've got your degree in chemistry and you want a job, there'll be people across the globe who will hire you because of your knowledge in chemistry. So yeah, you can travel wherever you like. It's really limitless.
Fantastic. That's great to hear. Right. It is 2:46. We haven't had any more questions come in, but it is 2:46. We are a minute over. Rob, thank you so much for coming to talk to us about chemistry. I've certainly enjoyed it, and I'm sure that the students have as well. Let me remind myself, we had it was the Sir William Ramsay School. If I've done my maths right, it's about 60 students, and I hope you guys have enjoyed it. And thank you very much for coming along, Rob, and talking to the students.
No, thank you for having me. I really enjoyed it. Thank you.
You're more than welcome. And thank you to the students as well and their teachers for interacting, asking questions and engaging. It's been really useful. Thank you very much to everybody. I hope we've all enjoyed the session. Enjoy your afternoons. And yeah, and Louisa has said such a brilliant talk. Thank you very much, Rob. So there you go.
Thanks for having me.
Thank you very much, guys. Have a good afternoon, everybody. And whoever is on, we'll see you in the next lessons tomorrow. Thank you.
Thanks, guys.